Swayam Prabha. Digital India. Educated India.
Hello and welcome to the discussion sessions of the production technology course, theory and practice. Now, I would like to remind you that what we have discussed last time after the friction in metal cutting and then practical machining operations like drilling, turning, milling and so on, and there we have seen that how the power can be estimated, how the material removal rate can be estimated, okay, and how the forces are involved in each of these cases like turning, shaping, planing, drilling and milling. Now, we said that these forces are to be measured, okay, and the device in the lab used for measuring the cutting forces is the dynamometer. Okay. Now, the dynamometer can be used for measuring forces in all the processes, all right. However, since the forces are different or differently located, differently directed in the turning, shaping, planing, drilling, milling, grinding. So, in that case probably for each of these processes we have to actually figure out that what kind of dynamometer to be used, or we have to actually design kind of a dynamometer that has to be used for a particular. Then we started discussing the, if you look at this slide, we have discussed the axially loaded member, and here is that axially loaded member which is and here is the load. Okay. So, what was said is that there are strain gauges or overall gauges. Okay. These are the strain gauges, or as I said that this can be the piezoelectric elements. So, these strain gauges are mounted diametrically opposite directions 1 and 4, and then perpendicular to that direction will be 2 and 3. Okay. Now, when the load will be applied, axial load will be applied, then the strain, okay, strain will be, axial strain will be measured by 1 and 4, and 2 and 3 gauges will measure the circumferential strain, and that circumferential strain, this is the result of the Poisson's effect. Okay. Then it was discussed that if these strain gauges are arranged in this way in the form of a Wheatstone bridge, in that case the strain that is given by 1 and 4, which will be the axial strain, that will be equal to the force divided by area and the E, modulus of elasticity of this material, okay, the material of the member. Now, again it was said that suppose there is a bending load, okay, or load perpendicular to this, for example. So, which will try to bend this way. In that case what will happen is that 1 and 4, since they are in the opposite arms, okay, then the strain that is occurring here, the additional strain of gauge 4, okay, being located diametrically opposite to 1, this will then have an equal and opposite strain, and the effect will cancel out in the bridge. Okay. So, therefore, what was said is that 1 and 4 strain gauges, they will exclusively sense the axial force and no other force will be sensed by 1 and 4. Okay. Similarly, since 2 and 3 they are diametrically opposite located in a diametrically opposite positions from each other, then the circumferential strain will be measured by 2 and 3, and no other force will influence on the 2 and 3, meaning that particularly the bending load, for example, because there will be an opposite effect here. They are also located diametrically opposite from each other, and it will be only the circumferential strain caused by the Poisson's ratio that will be measured by 2 and 3 strain gauges. Okay. So, 2 and 3 will give you this amount multiplied by the Poisson's ratio, which will be Poisson's constant, okay, or it is called the Poisson's well, I mean this is the Poisson constant. Okay. Now, this is in the negative with a negative sign E2 E3. All right. Next, let us see the measurement of cutting forces in with the help of a cantilever beam. Okay. So, this is the cantilever beam shown here, and let us say on this cantilever beam there are two opposite forces. So, let us say if this is the cantilever beam which is fixed on one side, then there are two loads, one vertically located, okay. Another one is the vertical to that at a 90-degree angle to that is located like this. So, one which will actually try to bend in this plane, bend the cantilever in this plane, and another force which will try to bend the cantilever beam along the another plane, and those two planes are mutually perpendicular planes. Okay. In that case, let us say to show these two forces, that is Fp and Fq. Okay. Here of course, that Fq is shown, and Fp will be not visible because it is perpendicular to this axis in another plane, in a plane perpendicular to the plane where Fq is located. So, let us take a cross section here. If we take a cross section, it will be shown like this, and Fq, this force is located here, and the another force which is perpendicular to this will be seen in this cross section as the Fp, which is shown here. All right. Now, in this cross section, what is shown is that the this bar or the cantilever beam, this has a this height is the h, okay, and the height and the dimension opposite to that on the 90-degree at a 90-degree to that is the b. So, this is the b and this is the h, which is the cross section of this beam. Now, to measure these forces Fp and Fq, we can have two sets of 4 strain gauges, okay, 2 sets of 4 strain gauges, so that both Fp and Fq can be measured. So, if you see here, these are the 2 strain gauges which are showing the 2 sets of 4 strain gauges, okay, 1, 2, 3, 4. 1, 2, 3, 4 will be glued on the or attached on the on this surface 1, 2, 3 and 4. So, here you can see that 1, 2, 3 and 4. All right. On this face will be 1 prime, 2 prime on the other side, 3 prime on the other side and 4 prime here. 1 prime, 2 prime on the other side, 3 prime on the other side and then 4 prime. So, 1, 2, 3, 4, these strain gauges will sense the force which will try to bend the cantilever beam because of the Fq, agreed. And similarly, 1 prime, 2 prime, 3 prime and 4 prime, these sensors or these gauges will sense the force which will try to bend the cantilever beam because of the Fp. All right. So, Fq will be sensed by 1, 2, 3, 4 and Fp will be sensed by 1 prime, 2 prime, 3 prime, 4 prime. Now, if we make 2 Wheatstone bridges, okay, one Wheatstone bridge consisting of 1, 2, 3 and 4 and another Wheatstone bridge comprising of 1 prime, 2 prime, 3 prime and 4 prime, then the strain that you can measure in that Wheatstone bridge, which is one comprising of 1, 2, 3, 4, that from there you can find out what is the value of the FQ. Okay. So, E1, E2, E3 and E4 in this Wheatstone bridge, okay, this is 1, 2, 3 and 4. This will be equal to, well, general formula is sigma I by E. This is the strain is the stress by modulus. Okay. So, therefore, the stress is equal to stress overall is equal to 6 m moment by BH square. BH square are those dimensions. So, this you can you probably have learnt in the solid mechanics course, all right. Now, m is the moment. Now, if the point of application of the force is known, so in this case Fq is located or applied at a distance of small l, let us see here. Let us say this is the small l from the sensor where the force has to be sensed. Okay. So, if it is known, then whatever moment is here, it can be written as this is the 6, m is this f, some f, whatever f it is, okay, f and the l, f and the l is the moment divided by BH square. So, therefore, the strain can be written as, you have the 6 FL divided by E and the BH square. We are putting the value of the sigma I here. Okay. So, this formula we are using to find out the E1, E2, E3 and E4 strain shown by the Wheatstone bridge, which is here. So, this will be equal to 6. Now, this F, since the 1, 2, 3, 4 will measure Fq. So, therefore, this force will be Fq, and this distance is small l from the point of application of the force up to the sensors or up to the gauges, and divided by E and the BH square. Okay. Similarly, on the other plane, you understand that BH will be interchanged, all right, because it is the other plane. So, there the E1 prime, E2 prime, here E1 prime, E2 prime, E3 prime and E4 prime, similar to this equation, it will be 6 and it will sense the Fp. So, therefore, we will in the place of F we will put the Fp. Again the small l will be the distance, because from here point of application of the force is here. So, from here to here is distance is small l anyway. So, we will take the small l divided by E and they will interchange places, okay, E h b square, all right. So, we will be knowing the strain we can find out from here, and E is the material property of the material that we are using in the cantilever beam, okay. B and H, these are the physical parameters that will be given by us, and L will be known. So, E, if we are measuring, Fq being unknown and all other parameters are known. So, Fq can be found out from that strain that you have measured multiplied by E, B and the H square divided by 6 into small l, that is it. So, here also similarly you can find out the Fp in the same way by measuring the strain here from here, and that multiplied by E h b square divided by 6 l. Okay. So, as you can see that in this case what is happening is that we are saying that if the point of application of the force is known, then the moment can be found out, and from the moment indirectly we are finding out what is the amount of force which is acting. Okay. So, this is the easiest way, this is the one of the easiest ways to actually find out or to measure the forces, and this is the principle which is used in the dynamometer, which are the devices which are used in the laboratories. Okay. Now, let us see the measurement of cutting forces when there is a ring type structure used. Okay. Here you can see that there is a ring type structure, and this ring type structure is rigidly mounted on the base somewhere, all right, and this structure has the pitch circle diameter, this is 2r, and it has the width which is small t, all right, okay, thickness, and the width of this is the b, because it has been shown in this view, it is the b. Now, here in this, it has been seen from the photoelastic studies, okay, the thin ring elastic theory and the photoelastic studies, that the strains maximum, the nodes where the maximum strain will be occurring, this will be at a 90-degree angle and at an angle of 39.6. So, this is not for all the structures, this is particularly for the structure that we are talking about, this is a ring type structure, and these ring type structures go through the photoelastic studies to find out what will be the what are the nodes where the maximum strain can occur. Okay. So, this is for the purpose of fixing or putting the sensor particularly in those positions. Okay. So, in the ring type structure, we will have the gauges on pasted on 1, 2, 3 and 4 at a 90-degree angle, and at an angle of 39.6, because these are the nodes, okay, B prime and the B, these are the nodes where there will be maximum strain, all right. So, therefore, AA section in the ring and the B prime section and the B section will have the two sets of 4 strain gauges, that is 1, 2, 3 and 4, and here you can see in the other cross section, other view, these are the all the 4. So, it will not, all 4 will not visible of course, and in this cross section, in this view here you can see that these are coming and visible here, all right. So, we will have the 1 prime, 2 prime, 3 prime and 4 prime, this will be attached here in these nodes, and in the along the 90-degree we will have 1, 2, 3, 4, and 1 prime, 2 prime, 3 prime and 4 prime, they are at the 39.6 degree. Okay. So, we will have 2 strain gauges, that is 1, 2, 3, 4, consisting of 1, 2, 3, 4, and 1, 2, 3, 4, these gauges of course will sense, as you understand, this force. Okay. This is the F perpendicular to this axis, and this is the normal force, okay, or the thrust force, sometimes we call it also. Now, the Fp, this is the tangential force, this will be sensed by the sensors which are given in the 1 prime, 2 prime, 3 prime and 4 prime, all right. Well, why it is that? Let us see, here we have shown 2 diagrams, like when the Fp is Fq, thrust force is acting, the ring will be deformed in this way, all right. Then the maximum deformation or the maximum strain can be obtained along this axis or along this section, this AA, right. Similarly, when the Fp is acting, that is the tangential force, the ring will be made like this. Now, suppose we, here it is the force which is acting is like this, right, and here this is the Fc. Oh, here it is written Fp, okay, Fp, but the direction is not given. So, the force will be like that, okay, and Fq will be the thrust force vertically located. So, if you see here that because of the Fp tangential force which is acting here at this point, the ring is the shape of the ring will be like this, all right, because it is mounted here rigidly, it is fixed here, all right. So, therefore, the maximum strain has been found out to be occurring along these points, okay, 39 at an angle of 39.6 degree. This, as I said, and I am repeating, this is it is the photoelastic experiments, okay. These notes are revealed. Now, the rings overall, this kind of structures provide a high ratio of sensitivity to stiffness, and at the same time have adequate stability against buckling. Okay. Buckling means that Fq is acting, that is the thrust force, and it will not break. Okay. So, it is a very sensitive, in the sense that a small force will also be sensed, okay, and the stiffness and very high force when it is imparted, it will not lose its stiffness, okay, and it has the ability to buckling, as we said. When the ring is subjected to normal force, let us say this is the Fq, inside of the ring will be subject to opposite state of strain, okay, from the outside. When the Fq is acting, then whatever strain will be coming on the outside, inside will be opposite strain. Okay. Hence, 4 active strain gauges can be located at 1, 2, 3, 4, so that Fq can be sensed, and at 90 degree, okay, the strain that can be measured from the formula here. This formula is taken from the thin ring elastic theory. Okay. So, this is the thin ring structure. So, therefore, the thin ring elastic theory says it is this, and this is the coefficient 1.09, and this is Fr. So, F in this case will be Fq, all right. This is the normal force, or this is the thrust force, as I said, and E is the property of this modulus of this material of the ring. Okay. B and T, B is this width and T is the thickness here of the ring, all right, and R is the from the center to the pitch circle. Pitch circle is the mean circle, all right. This is the R, that is the half of the diameter of the ring, and the diameter of the ring is neither outer nor extra, not inner. This is the up to the pitch circle, all right. That is how the thin ring elastic theory suggests, all right. At 39.6 degree, this formula is coefficient is different, although the formula is the same, but the coefficient is 2.31 plus minus, okay, and using this formula the strain here can be measured, if or rather the strain will be measured here. We will get a strain value, all right, here. Now, from here, from using this formula, we can find out the force, because ultimately what we are getting is, what we are trying to say is that we are trying to measure the forces. Okay. So, here in these cases, in the case of dynamometer, we are measuring strain as output, and from that strain we are finding out what will be the value of the forces, either the normal force or the axial force which is imparted on the ring dynamometer. So, that means this E90 we can actually measure from here, all right, from this galvanometer. So, put that value here, okay, that multiplied by E, B and T square divided by R and the 1.09. So, then you can find out what will be the magnitude of the Fq, isn't it. Similarly, you find out the 39.6 degree strain, all right, from this Wheatstone bridge, and from here this value is known then, because from the galvanometer you can find out that strain, and then you multiply by EBT square divided by 2.31 R, you can find out what is the value of the Fp, which is the axial force. Okay. So, this is how the structures are used so that the forces can be actually measured. Okay. Now, let us see in this slide we have the measurement of cutting forces using an octagon type ring. Okay. Now, if we come back and see this ring type structure, it has a tendency of rolling. You can see this. For example, if the when the Fp is acting, it has a tendency to roll along the horizontal direction. Okay. Although we said that on the buckling it is fine, it does not have any problem, and it has a high ratio of sensitivity to stiffness, but still it has a tendency to roll, and that is why, or rather you can say that they are not very reliable in case of forces when they are high in magnitude, because high magnitude force will actually try to roll it, and then it will give you the error in the measurement of the strain. So, to strengthen the structure, we have the octagon type. You can see that this is actually the modification of ring type structure. Okay. But only thing is that here in this structure, the strength of this structure has become more by giving the octagon shape of to the ring. All right. Now, the photoelastic examination of such rings, they actually reveal that here the strain nodes are like 1, 2, 3, 4 at an angle of 90 degree, okay, and 1 prime, 2 prime, 3 prime and 4 prime, these are at an angle of 50 degree. All right. Now, we come back and here we can see that here it is 1 prime, 2 prime, 3 prime and 4 prime, they are at an angle of 39.6 degree. By the way, this this can be also put in here as well, okay, but here we are putting it on the opposite side because to compensate for this, for the other forces rather than the force that we are measuring, okay, the one that we have already talked about earlier. Now, the here it will be at 90 degree and at an angle of 50 degree. So, in this case, as you can see, the sensors are attached as 1 prime, 2 prime, 3 prime and 4 prime for at an angle of 50 degree for forces which we are measuring in FQ and the FP. So, FQ, all right, FQ, which is the thrust force or normal force, that will be sensed by sensors which are attached at an angle of 90 degree, 1, 2, 3 and 4. And the axial force or the tangential force FP, this will be sensed by the sensors which are attached along the 1 prime, 4 prime and 2 prime, 3 prime or along this axis, that is 1 prime, 2 prime, 3 prime and 4 prime. Okay. And these axes are at 90 degree with respect to the vertical axis. With respect to the vertical axis, it is at 50 degree angle. Okay. This is at that angle 1 prime, 4 prime and 2 prime, 3 prime, they are attached, fixed. Now, if you take two Wheatstone bridges similar to this, that is one which comprises of 1, 2, 3 and 4 and another which is 1 prime, 2 prime, 3 prime and 4 prime for this, all right, then that Wheatstone bridge which is of 1, 2, 3, 4 gauges, that will measure the force which will be FQ, okay, thrust force. And this formula from the again thin ring elastic theory we have taken. So, this you can see that this is the same 1.09 because this is the angle 90 degree. So, here also it is at 90 degree. So, therefore, plus minus 1.09 FQ, because 1, 2, 3 and 4 they will actually measure the FQ, which is the thrust force, all right, and here rest of the things will be the same as in case of the ring, all right. And here for 50 degree, that is 1 prime, 2 prime, 3 prime and 4 prime, the strain that will be measured by the Wheatstone bridge comprising of 1 prime, 2 prime, 3 prime and 4 prime, it will have the formula like this, and from this formula you can find out the value of the FP, because 1 prime, 2 prime, 3 prime and 4 prime will sense the force which is FP. This is the axial force or this is the tangential force, all right. So, you can see that only thing that has been changed is that we have strengthened the structure, and because of that the photoelastic experiments have shown that the nodes have changed. Instead of 39.6 in the case of the ring structure, here it is the 50 degree angle. So, we are placing the sensors at a 50 degree angle, so that the maximum E can be obtained here. With this formula we can find out, okay, these formulas we can find out the appropriate value of the FP or FQ by measuring the strain which is coming from the Wheatstone bridge, comprising of 1, 2, 3, 4 or comprising of 1 prime, 2 prime, 3 prime and 4 prime. Well, now here you can see that this octagon is also not very rigid when the large forces are acting, when the force values are very high. So, we will see later that at certain point that how to increase the rigidity of this. Now, for the measurement of cutting forces, the dynamometers that are used, those dynamometers have certain requirements, okay. And whatever is the dynamometer, it is either it's a ring type dynamometer, or it's a cantilever beam dynamometer, or it's a octagonal dynamometer. All these requirements or all these demands, okay, should be there. So, first is the sensitivity. Now, the sensitivity means that they should be highly sensitive. Even a small force which is acting on the dynamometer, it should actually able to sense, and it should be able to sense properly, correctly, okay. It should not have the error in the reading. Second is the rigidity. Rigidity should be sufficiently high, okay. So, dynamometers should be sufficiently rigid relative to the rest of the machine tool, so that it does not affect the cutting condition by causing excessive vibration and chatter, okay. So, what we mean to say is that the dynamometer is attached to the tool post. Let us say we are talking about turning, all right. In case of turning, the dynamometer will be placed on the tool post and the tool will be attached to the dynamometer, all right. And of course, you understand the tool will be hanging in that case, and we will see that the dynamometer then will be made of the cantilever beam type, okay. Let us say for example, in case of drilling. In case of drilling, since the force is applied by the drill, that is the thrust force and the torque applied by the drill to the workpiece. So, the workpiece has to contain the dynamometer, okay. So, the dynamometer has to be attached to the workpiece. So, therefore, on the table on which the workpiece is mounted, the dynamometer is fixed, and then on top of the dynamometer the workpiece will be fixed, so that the forces which are applied to the workpiece can be transmitted to the dynamometer, and so that the dynamometer could sense the forces, okay. So, therefore, it is told here that this rigidity should be sufficient, the rigidity of the dynamometer, okay. And that dynamometer, when it is attached to the tool post, should not cause excessive vibration or self excited vibration, which is chatter, all right. In order that the interference with cutting condition is small, the natural frequency of the dynamometer should be several times the cutting frequency, okay. What it is meant is that when you are fixing the dynamometer on the tool post, let us say, or tool post is on the dynamometer, whatever is the case, in that case that is an additional mass attached, okay. And that additional mass should not have a natural frequency which is equal to the natural frequency of some parts of the machine tool. In that case, you understand that if it is so, then there will be resonance, okay. And therefore, the natural frequency of the dynamometer is selected very different or much away from any of the natural frequencies of the components of the machine tool. By machine tool component, we mean that natural frequency of the headstock or the tailstock or the bed, okay. In case of turning, I am talking about. Similarly, in case of column, in case of arbor, in case of the gear drives, spindle and so on, for other machines like milling, like drilling and so on, okay. Third requirement is the linearity, and the linearity is the relationship between the magnitude of the cutting forces and the deflection that should be perfectly linear without any hysteresis effect. So, what is said is that the curve, which is very important, that in this axis suppose we have cutting force, okay, either it can be Fc or Ft or whatever, and this is let us say deflection here in this x axis, deflection is let us say delta. So, this cutting force and deflection should be exactly linear. Okay. That means, as the cutting force is increasing, the deflection also is increasing linearly. You can put the deflection here, cutting force is here, does not matter. So, it should not have any hysteresis, in the sense that if the f is removed, it should come back along the same line, all right. And you know the it should not have any hysteresis kind of thing. Okay. This should not be, this is not allowed. So, it should be exactly linear, that is what the linearity means. Now, the next is the interaction. There should be negligible cross sensitivity. By cross sensitivity, we mean, we have already said that about the cross sensitivity in case of the first case, that is when the cylindrical job is, you can see this for example here in the axially loaded member, the cross sensitivity is that 1 and 4 should not have any other values or any other influence of any other force, bending force, or the 2 and 3 should not have the influence on the 1 and 4. Okay. Here for example, when you are measuring FQ, all right, 1, 4, 2 and 3 only will sense the FQ. 1 prime, 2 prime, 3 prime and 4 prime will not sense anything, and vice versa. That is, when you are measuring the FP, 1, 2, 3 and 4 will not show anything. So, this is the cross sensitivity, that when you are measuring one force, that will be sensed only by a particular set of transducers or the gauges, and other gauges will not be affected, not show anything. Okay. So, now next is the stability. It should be sufficiently stable, so that it does not disturb the machining process, because instability in the process will actually give rise to the vibration, to the chatter, self excited vibration and so on. So, that is a long story. So, we are saying that the dynamometer should have very stable and have a high stability. Now, the machine tool dynamometer, actually this is disturbing. So, I will just remove this. Machine tool dynamometer, if you see here, these are the designs here. Here what is shown is the dynamometer that is used in turning. Okay. So, this is the fixing of the cantilever beam type. Okay. So, let us say here it is the tool post, and let us say this is the tool post. Okay. And on this we have the dynamometer along with this. So, a part of it will be the dynamometer, of course, all right. And at the end of the at the end of the cantilever beam, we have the tool fixed, all right. And inside this dynamometer, we will have the strain gauges, or of course, in the modern dynamometers, like the dynamometers made by the Chrysler in Switzerland. So, those are they actually have the monopoly. So, best dynamometers available so far in the world is the Chrysler make dynamometers, and those dynamometers now are using piezoelectric elements. They do not use the strain gauges, because strain gauges, because of their disadvantages that I already told you, that they can be torn somewhere, those wires, or they do not work in the high temperature environment. So, the piezoelectric elements are used in the dynamometers, and these are these can be the piezoelectric elements, all right. Now, when it is subjected to forces like FQ and FP, which we have shown in the cantilever beam type of the dynamometer, Then the sensors or the piezoelectric elements which are mounted on this surface, okay, of the tool post, okay, on this surface of the of the cantilever beam 1, 2, 3 and 4. These sensors will sense the force acting like this, okay, that is the thrust force Fq, and the Fp which is perpendicular to this, this force will be sensed by 1 prime, 2 prime, 3 prime and 4 prime. Other 1, 2 prime and 3 prime are at this face opposite to this, you understand that. Okay. So, you make two strain gauges 1, 2, 3, 4 and 1 prime, 2 prime, 3 prime, 4 prime if it is strain gauge, or otherwise if it is piezoelectric element. So, with the help of the preamplifier and then the amplifier, you can actually find out that what is the strain which is occurring here, all right. So, both way, either it is with the help of the strain gauges or with the help of piezoelectric elements, you can find out the magnitude of the Fq and the Fp indirectly from the moment and from the strain that you are measuring, either from the Wheatstone bridge in case of the gauges, in case of the strain gauges, or with in terms of the curves which the output of the dynamometer will give. Okay. Now, here if you can see, here is the kind of the ring type structure that we have seen, and this is the view of the dynamometer or inside view of the dynamometer, which is used for measuring the forces in drilling. Now, let me tell you that coming back to the machine tool for the dynamometer of turning, these are the forces which are typical for the turning, all right. This is the thrust force and this is the this is the cutting force and the thrust force, okay, cutting force and the thrust force. So, these forces are different than the drilling forces. In drilling, as we have already discussed, that the thrust and the torque both are applied to the drill. So, therefore, if you have a dynamometer like that, it is very obvious that this cannot be used for the drilling, for measuring the drilling forces in drilling. Okay. But if we have a dynamometer like this, here if you can see that this is the dynamometer and this other view is the ring type. So, this has a ring and this ring will have the spikes. Okay. So, this is these are the kind of the arms or the spikes, okay. And inside at the middle, this is the solid body. So, this is solid body, these are the spikes which are solid, all right, arms. Now, on these arms, 4 arms, we will have rather we will have 16 strain gauges, let us, okay, 1, 2, 3, 4, 5, 6, 7, 8, and similarly we will have 9, and on the other side it is 10, 11, 12, 13, 14, 15, 16 and so on. So, there are 16 elements of gauges or piezoelectric elements which actually will sense 2 types of forces. One is the torque and another is the thrust force, which helps the penetration of the drill to the workpiece, all right. Now, if you see the thrust force which is applying like this, all right, it will be sensed by the sensors which are located after 8, that is 9, 10, 11, 12, 13, 14 and 15, 16, because when the thrust force will be acting, it will be vertical to this, all right, it will be you cannot see it here because it will be vertical, and then in this plane where we have the 9 to 16, these are the elements which will actually be affected. So, therefore, 9, 10 and here you can see that these are the 13, 14. So, 11, 12 and 15, 16 are here. So, if you take the cross section here along this, you will find that here you can see the 9 and 10, okay, 9 here and on the opposite side it is 10. So, because we have taken, actually this is the cross section, okay, and the cross section is taken like this, through this, okay, here. So, let us say this is x x and this is x x, all right. So, here we can see the 9 and the opposite side is 10, and here suppose we have 13 and opposite side we have the 14, all right. So, that is about the 9 to 16 when the thrust is acting. Now, when the torque is acting, as you understand that suppose if there is a torque acting here, so then these arms will be affected in the bending, these arms will be bending, all right, and 1, 2, 3, 4, 5, 6 and 7, 8, these are the sensors which will then sense this kind of a torque which is applied. Okay. So, this is the T torque which will be sensed by the 1 to 8, these are the sensors. Okay. I hope this is understood, that here the dynamometer will be placed on the top of the workpiece, will be placed on the top of the dynamometer. So, let us show it like this. Let us say you have to drill a hole here, all right, this is the workpiece. So, this is clamped, of course, okay, this is clamped, and the it will be drilled. So, when the drill has penetrated or drill is penetrating, the force which is acting on this will be imparted on this. These are rigidly fixed. This is the workpiece. This is the workpiece, and this is the dynamometer. Okay. So, the forces which are acting, let us say this T, this will be acting on through the workpiece on the dynamometer, and then the dynamometer, it will help, this force will help to deform the arms, okay, in this direction, okay, that it will be deformed like this, all right. You understand that the force is acting like this. So, the arms will be deformed in the horizontal direction, and similarly when the torque is applied, it will be deformed in the vertical direction. Okay. So, therefore, two opposite direction sensors, they will sense, like 1, 2, 3, 4, 5, 6, 7, 8 will sense the torque, and 1 prime 9, 10, 11, 12 up to 16, these are the sensors which will sense the thrust. So, again you have two Wheatstone bridges, one comprising of 1, 2, 8, and in that case, of course, you understand that we will have on each arm we will have 2, okay, like this, because earlier we had 1 and here also. So, these are the 8, that is it. So, here you have the galvanometer and here you are giving the feeding, all right. So, this is, let us say 1, 2, 3, 4, 5, 6, 7, 8, keeping in mind then of course that this will be opposite. So, I am not maintaining according to this, but I am saying that they have to be opposite located to the opposite directions, because of due to so that it can nullify the other effects, all right. So, 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8 will actually measure the torque once again. A similar Wheatstone bridge can be made, okay, of 9, 10, 11, 12, 13, 14, 15, 16, which will actually sense the thrust, all right. Now, this of course, when the dynamometer will have the strain gauges, when the dynamometer will have the piezoelectric elements, of course, these elements will be connected to the preamplifier initially, output of the piezoelectric elements, and after the preamplifier it will be amplified, and that signal can normally that signal goes into the personal computer, laptop or a PC, and in the PC you can see actually the curve which will show you on each axis fx, fy, fz how the forces are varying, okay, with cutting time. and that's a very easy to monitor that way, because you are directly getting the curve, that is how the force is changing, or how the force behaves as the cutting process goes on. Okay. So, you can find out also the magnitude obviously of the force, that is basic purpose, that what is the magnitude of the force. All right. Okay. This is the structure which we are familiar with. We have seen that one of them, the smaller version of that, is the octagonal dynamometer, and octagonal dynamometer we said that itself is a modification of the ring type dynamometer. Okay. So, here the octagonal dynamometer has been further modified, you can see this. Okay. Now, here the rigidity of the octagonal dynamometer has been increased. So, the structure is like this, that we have the octagon, but this is an extended octagon, therefore, it is called the extended octagonal ring dynamometer, because principle is of the ring dynamometer, but this is and not simply octagon, but this is extended octagon. So, therefore, all the principles of the octagon structure that we have discussed is remaining the same, means that at a 90-degree angle you will have the 1, 2, 3, 4 sensors, and those sensors will sense the thrust force. Let us say in this case it is the Fp or Fq, and Fp, this is the tangential force, this will be sensed by the sensors which are located at a 50-degree angle. If you see this is 50-degree angle for the octagon. Okay. So, therefore, in the extended octagon also this will be at a 50-degree angle, because this the principle is the same, and 1 prime, 2 prime, 3 prime and 4 prime, these sensors will sense the F, this is the tangential force, okay, one of them, let us say I do not know, this may be Fp. So, Fp we are sensing by Fp is sensed by 1 prime, 2 prime, 3 prime and 4 prime, and Fq, which is the thrust, this is sensed by 1, 2, 3 and 4. Here, as you can see, that the entire structure, the dynamometer is fixed on the base, on some base. So, this is fixed on the table. Okay, this is the machine table. Okay, and on this the workpiece will be fixed, like in case of the drilling we said. Okay, this is workpiece. So, let us say this is a flat workpiece, and the milling cutter starts working, okay, because this is normally used for milling or the grinding. So, this will be rotating like this, and this will be fed here along with this, because it is fixed. All right, workpiece is rigidly connected to the dynamometer. So, this is the dynamometer. Okay. This is the dynamometer. Dynamometer is rigidly fixed with the on the table and rigidly fixed with the workpiece. So, workpiece is rigidly fixed on the dynamometer rather. So, therefore, if the when the milling cutter, this is the milling cutter, or by the way this can also be grinding. Okay. This can also be used for measuring the grinding forces. So, this is the milling cutter or grinding wheel. Okay. Grinding wheel can also be used, because principle remains the same. In case it is the this is used for measuring the grinding forces, in that case the same thing on the grinding machine table, the dynamometer is rigidly fixed and the workpiece in its turn is rigidly fixed on the dynamometer. Okay. So, circular or octagonal rings are not useful by itself, okay, but can be made sufficiently stable by extending it. Okay. I will once again remind you that here we have the circular ring type structure, and here we said that although these structures are rigid are rigid enough and they can withstand lot of force against buckling, buckling does not happen. But in these cases when the ring type structures are used, they have a tendency to roll at this horizontal surface. So, you can see that if the tangential force is applied, in that case it will have a tendency to roll. So, therefore, this to overcome that, or for octagon for example, the rigidity is not enough. Let us say when we are using this kind of octagonal structure in the dynamometer for grinding, in case of grinding the forces may be very high. Okay. In case of milling, the forces may be very high, and the octagon structure itself may not be able to withstand the magnitude of forces which are applied on the milling during the milling process or during the grinding process. In that case, what is done is here, that is, it is extended. So, by the way, here actually this is do not get confused, that this is the metallic part. Okay, this is metallic part which is connected here, this is all metallic part. So, that is why let us say I will hatch it because it is in the section now, I am sectioning that, and this is a hole, this is nothing is there, and as you can see that by making this slot and connecting these holes, all right, we are actually giving the giving more rigidity to the more flexibility to the dynamometer. Okay, these all metallic. So, now what happens is that it is more flexible as well as very rigid, because it has a lot of, it is a very good rigidity, overall strength. Now, this hole and this slot, this will actually also give the flexibility, so that a small amount of force actually acting, either it is a thrust or it is an axial force, tangential force, they can be easily sensed by the dynamometer. That is the idea. So, here if you see the the purpose of the ring type dynamometer, which is not very comfortable to be used for the milling or the milling or the grinding, or the octagonal ring type dynamometer, these principles are used here, but in a better way. So, in a developed way, let us say, so that the rigidity becomes more and the sensitivity of this dynamometer becomes more. They are more sensitive, very sensitive because of the structure itself. So, now out of all this, here you can see this, that as I said, that suitable for horizontal milling, horizontal surface grinding, etc. Okay. Now, here you can see one thing that I already mentioned earlier, that these dynamometers, that is drilling, okay, turning and then milling or grinding, these are dynamometers only for these purposes, meaning that here this dynamometer cannot be used for drilling dynamometer cannot be used to measure forces in turning, or drilling dynamometer cannot be used here also. Okay. But these days there are universal dynamometers which are also made by the Chryslers, where you can measure the forces in both, let us say, turning and drilling and the milling. Okay. Those are more expensive, of course. So, rest of the topics in this discussion series, I will discuss it with you in the next session. Thank you for your attention.